Greetings and welcome back. Today we'll be looking at how you identify exactly which molecule you have if it is a chiral molecule. So for instance, we've named molecules already, 2-propanol, etc., etc. However, we've seen that some molecules can be chiral, that is to say, they might be right-handed or left-handed, and none of the naming we've done up to this point will differentiate your right hand from your left when it comes to molecules. So today we'll be looking at how exactly we can do that. So we're going to start with an example of a molecule that we haven't named before, but it's pretty simple to do so. Let's do this guy. So this is an alcohol, specifically it's a 2-carbon alcohol, so it's an ethanol. So this would be a 1-fluoroethanol because it's a molecule that has 2 carbons. And it has the fluorine at position number 1. So that's how you name alkyl halides in general. They're quite simple. But this is a 1-fluoroethanol. All right, you can tell that this carbon right here, number 1, is a chiral carbon. It has 4 different substituents because it has the fluorine, the alcohol, a CH3, and an H. So that, therefore, is a chiral carbon. And let's talk about how we can identify exactly which molecule that is. So there's a right-handed and a left-handed version of 1-fluoroethanol. All right, so I'm going to draw this one again, a little bit larger. I'll have the H there, the fluorine on the dash, the OH off to the right, and the CH3 off to the left. All right, and so there's rules that we go about in order to identify which enantiomer or which chiral molecule this is. So essentially it's handedness, whether it's a right-hand or a left-hand version. And the way that we start with this is it proceeds through 3 rules. The first is that we rank the 4 substituents from number 1 to number 4 based on atomic number. All right, and atomic numbers, of course, that's just the number above the atomic symbol in the periodic table. But we can look up here on the periodic table, or if you have one near you, and you can tell that fluorine has the highest atomic number between fluorine, oxygen, carbon, and hydrogen. So therefore, if we're ranking these, fluorine would be number 1, oxygen would be number 2, carbon would be number 3, and hydrogen would be number 4. And again, all the way that we get that is we just look at the atomic number on the periodic table. All right, the second thing that we do is we rotate the molecule so that whatever your number 4 substituent is going back. That is to say, it is on the dash. So in this case, you'll notice that the number 4 substituent, which is the hydrogen, and often the number 4 substituent is hydrogen because it is the lowest atomic number on the periodic table. We have to rotate that guy and put it in the back. So what we want to do is pick an axis to rotate this around. And I would always suggest that you pick an axis that is one of the kind of straight bonds. So we're going to pick this methyl group right here as our axis. And we're going to rotate the other 3 substituents around it. So we want to push number 4 to the back, which would push fluorine over to this straight bond on the lower right, and it would push OH up to the wedge. And so let's redraw that again after we have done this rotation. So whichever substituent is on your axis will remain in the exact same spot, and all of the bonds will remain in the same spot, but what's at the end of those bonds for the 3 that have rotated will change. So we push the H to the back, so the H is now on the dash. We move the fluorine down to the lower right, and we move the OH up to the top left. And we're going to go ahead and put the numbers back up there again, because the numbers have moved as well, but they're still the same. So fluorine is still number 1, OH is still number 2, or specifically the O, the hydrogen is still number 4, and the carbon is still number 3. All right, so then moving on to the next rule, which is the last one, we are going to draw an arrow from 1 to 2 to 3. We don't include number 4 in that because we specifically, in step number 2, rotated this so that number 4 is just kind of going away from us. We draw that arrow from 1 to 2 to 3, and that's what we'll do right here. So here's number 1, there's number 2, there's number 3, and if the arrow is clockwise, then we designate that specific chiral center as R. And if the arrow is going counterclockwise, we designate it as S. So any chiral carbon will be either R or S. We can talk about what those stand for in class. I'll give you a hint, it's still not kind to left-handed people. But that is what we use. So each molecule can be an R or an S version of itself, or each chiral molecule specifically. So this one we can see is going from 1 to 2 to 3, and that's counterclockwise. So therefore this is an S molecule. So we can include that in the name up above. We would just say that this is S1-fluoroethanol. And so we put that just way out front of the name, kind of like we did with cis and trans. So that designates that this 1-fluoroethanol is S. Oh my goodness, I spelled fluoroethanol wrong. There's a U in there. It's fluoro. I apologize greatly for that. All right, so let's see how you can do, and then we'll move into a little bit more complicated examples. All right, so this is a pretty simple molecule. However, it adds a slight layer of complexity to what we're doing right now. And so this would be a chloropentane, specifically a 2-chloropentane. And I'll try to spell chloro correctly. Oh, I did it. Congratulations, Josh. All right, chloropentane. And because this would go from right to left since the chlorine is closest to the right. Okay, so let's go ahead and figure out what the stereochemistry of this is. Well, let's draw in our hydrogen. And this right here is our chiral carbon. And so that's the one where we need to rank things. So again, I'm going to draw this out a little bit bigger. But I'm just going to draw the first atom that's attached. So you'll notice if we do that, we can say for sure that our chlorine is number 1 and our hydrogen is number 4, but we have a tie because both of those carbons are carbons and you can't really differentiate a carbon from a carbon. Therefore, what we need to do is break the tie by looking at the next bonds. And besides where we came from, every carbon is going to make 4 bonds, so to break a tie between carbons, you need to draw the next 3 bonds. So the carbon on the right has 3 hydrogens attached. The carbon on the left has 1 carbon and 2 hydrogens attached. And so essentially we walk through this stepwise. We would say that these 2 carbons tied, and then we would proceed to look at the highest atomic number on the next substituent. So kind of think about this almost like a family tree, where what you're doing first is evaluating, starting at your chiral carbon, you're evaluating basically the atomic number of your children. So the first things first. But if your children tie, so you have 2 carbons that are tied, or anything else, it could be oxygens, then you are looking at the grandchildren, and you're comparing those. So we're going one more step. But you always start with just, excuse me for saying this, but the best grandchild, and you're comparing those first. If those were a tie, then you would look at the next one, and the next one. If all of those were tied, you'd keep moving on down the chain. If you end up with everything tied, that means that those 2 substituents are exactly the same, and therefore it's not a chiral molecule in the first place. All right, so this would mean that the left group is of higher priority than the right group, because while we were tied for that first substituent, the next thing down the chain had a higher atomic number, so carbon beats hydrogen, and therefore this is 2 and 3. You'll notice that in this case, number 4 is already in the back, so we don't need to do that's step number 2. We don't need to rotate it around. And remember, we would only rotate it around if we wanted to put 4 in the back, but 4 is already in the back, so we're good to go. We can skip that. So now we draw our arrow from 1 to 2 to 3, and in this case that arrow is going clockwise, so this would be the R version, the R enantiomer, and so therefore the name of this molecule would be R2-chloropentane. All right, so let me give you kind of one last example, and then I'll let you try it again, and we will move on. So this is an amino acid. Specifically, this is alanine, but you can see that it's going to have the amine and the carboxylic acid. All right, so we can rank these things. Once again, H is still number 4. The nitrogen, right, we're comparing nitrogen to carbon. Nitrogen would be number 1. Those 2 carbons are tied. However, the carbon on the left has what we would consider to be 3 bonds to oxygen. So if you have a carbon with a double bond, for the sake of prioritizing, we would count it as this, 3 bonds to oxygen. The carbon that's on the dash is a carbon with 3 bonds to hydrogen. And therefore, fairly obviously, the carbon with 3 bonds to oxygen would beat the one with 3 bonds to hydrogen because oxygen is a higher atomic number than hydrogen. So this would be number 2, and this guy would be number 3. All right, so as a little trick, we could rotate this around, but if perchance your number 4 is coming straight out at you, you can assume that you're basically looking at this from the wrong direction. So we want our hydrogen to be going away, but if our hydrogen is coming towards us, you know that basically it's completely reversed. And if it's completely reversed, we can reverse it again to reverse it back to normal. So it's kind of like 2 wrongs don't make a right, but if you commit 2 errors in terms of this, since there's only 2 options, we would be doing it wrong, and then if we did it wrong again, we would do it right. So I don't know if that makes sense, but hopefully. This is basically a hint that can help you out. You can, of course, go through the exact same rules that we did, or what you can do is say, well, if number 4 is coming out at us, then instead of drawing my arrow from 1 to 2 to 3, I should draw it from 3 to 2 to 1. And you will get the exact same answer. So this, you can see, is an S enantiomer. It's an S chiral carbon. So just to prove it to you, let's go ahead and walk through our rules the way that we should. And so I'm going to keep this right here as my axis. I'm going to rotate everything around. We want to push 4 to the 3. 3 is going to move over here, and 1's going to move up where the 4 was. So we can draw this again. We'll leave the carboxylic acid in the same place because it was our axis around which we rotated. The hydrogen moved to the back. The methyl moved down to the right, the bottom right, and the NH2, the amine, moved up to the wedge. So let's do our numbering again. The hydrogen is number 4, the amine is number 1, the carboxylic acid was our number 2, and the methyl was our number 3. And so when we draw our arrow, which again, in this case, because 4 is in the back, we go 1 to 2 to 3, you'll notice that it is indeed S. So either way you do this, if you use the shortcut, you get the same answer as doing it kind of the long way. I will warn you this won't work if the hydrogen is on one of the straight lines. So if the hydrogen was here or here, you couldn't do that. But if the hydrogen's going out at you, you can skip a step and just draw your arrow 3 to 2 to 1 instead, and it'll get the same answer. As it turns out biologically, all amino acids are always S, except for one of them. The one that isn't is glycine. Glycine is this. So I would like you to think about and answer in class, why is this guy not S? It's the only one that isn't. All right, thank you very much. Practice this out. Think about my random question, and we will get together soon.